Second of our robotics preliminary design presentations. This is the scenario group, and we'll be talking about the project, obviously. But I once again want to thank our reviewers for taking the time to be here today. We have Dr. Gordon Dr. Bruder, Dr. Davis, Dr. Skipper, Bryce Chanez, and Bryce Mills, who are our guest reviewers from industry. So thank you again for showing up, and I'm going to turn it over to the students.
Thank you, Dr. Ed. Welcome. My name is Andy Worthington. This is Timothy Anderson, Lorenzo Lucchesi, Maddie Markham, and Lucas Vasconcelos. And together we are Scenario Robotics, or the simulated control environment for active robots in orbit. Today I'm going to talk about our project overview and some of the background behind it. I'm going to talk about the design requirements and specifications that we've come up with to help us meet our goals. Then we're going to jump into the preliminary design. We'll talk about the mechanical, then electrical systems, our dynamic modeling and simulation, and then our system identification and control design. From there, we will conclude and go to questions. So to understand this project, it's important to know the background behind it. We're not the first team to work on it. Dr. Isenberg, Dr. Gentilini, and a graduate student, ERAU, paved the way in 2016 with a research paper with a novel concept. The idea that with a force torque sensor, by measuring those forces and having a speedy controller, they can accurately simulate a free-floating, frictionless environment for a space robot. So as you can see on the right here, this is a simulation that they performed with a Cartesian robotic manipulator, which translates in X, Y, and rotates. Additionally, they have a torque force sensor measuring the motion created by their planar space robot. Now, this was a comparison of a simulation. They actually simulated just the robot in space and compared that to the simulation of the combined dynamics of the whole. Later on in 2018, they published an experimental validation of this. This was very important because they actually constructed, pictured on the right is a Harada Cartesian manipulator. This translates in X and Y and rotates with a torque force sensor and the planar space robot on top. They found this had good agreement with their model. They found a little drift, and they introduced a novel control mechanism calculating the center of mass of the planar space robot with a known mass using the other two unused axes of the torque force sensor. One important thing to note is that this is all model-free. They don't have an equation of motion of this robot, and so it's generalized in that way. The only thing that they know for the second controller is just the mass, which is easy to measure. In this way, they compared the previous simulation of the free-floating environment to their experimental results from the combined dynamics of the whole. Enter project scenario. What we intend to do is we intend to replace that simulation of the free-floating environment with an experimental model. We are going to use the air bearings table with a planar space robot in a free-floating environment, and that'll be our truth. That'll be our control test. We are then going to compare that to our experimental setup with the Harada running as fast as it will be in history. And this is especially important for when we move on to the future. The hopeful future of this project is that it will move up from a planar environment into a three-dimensional 6 degree of freedom full space simulation. Now, there is no air bearings table equivalent for this. It's space. So it is especially important that our simulation produces good results and compares well to the theory so that we can trust the force torque sensor on the model in the future. To do this, we've defined several requirements and broken it up into 5 subsystems. Requirements are the high-level non-numerical goals of our system. The first and most important of these is that it simulates, the robotic platform simulates a free-floating environment for the planar space robot. This is going to do it in a 3 degree of freedom environment with full 360 degree rotation, X and Y translation. Next, our data acquisition system. This is going to consist of all of the sensors on our robot systems, including the encoders, the decoders, and the ATI Mini 40 force torque sensor pictured here. This is a very high-resolution force torque sensor that has been allocated to us by the Space Robotics Lab. The most important requirement here is the data acquisition system's data acquisition frequency. We want to go at a very, very high frequency to pick up all the high-frequency forces and torques in our models. Additionally, we're going to be using a motion capture system. The importance of this is that we'll pick up the task-based coordinates of the base of our robot on the air bearings table. When it's mounted on the Harada manipulator, we know where that is because of the encoders on the joints. But on the air bearings table, it's a little more abstract. And so we're using a motion capture system that's already set up in the Space Robotics lab to do this. Additionally, our software subsystem, we want this to be a utility, something that a team can use, put an arbitrary satellite on and get data from. And so to do this, we want to have some sort of user interface to make this easier. We want them to be able to set experimental parameters and move their robot around from our controller. Additionally, for our planar space robot subsystems, the most important thing is that we have 2 identical mass robots. We also want to make sure they have 4 identical links. This is going to be 2 arms with 2 links apiece. The reason for this is to up our complexity of the data that we're getting back and produce interesting results for our force torque sensor. Additionally, we want this to be similar to an actual satellite operating in a planar environment, and so we're going to be including some sort of attitude control. For this, we are using a momentum wheel to set our angle. Additionally, it's very important that we have at least 1 robot with functional air bearings so that it can be on the air bearings table. Also, we have requirements for no wires coming off of our robots, so we have everything contained. There are no external disturbances that we can't monitor. These are the most significant specifications. Our specifications are the numerical benchmarks that were designed to help us reach our goal. The most important is our data acquisition frequencies of our robotic platform. We want 1,000 hertz on that. This is a combined data acquisition and control frequency. This is especially important so that we pick up all of the possible forces and we reduce drift as much as possible. Additionally, on our planar space robots, we're shooting for 100 hertz control frequency. This is less important, so it's 1/10 of the previous frequency, but we're just moving motors. Additionally, the motion capture frequency is, we figured that 30 hertz is the minimum we want to go there. It's not being used for control, we're just using it for analysis after the fact. This specification is actually already met because our motion capture system that we're using runs at above 900 hertz. Additionally, the total mass error between our 2 robots, we've specified a maximum of 2%. This is mostly going to be included in the mass distribution, which is a little more difficult to measure on a robot as a whole. And while these are the most significant specifications that we've defined, all of them have been included in your handout, as well as the requirements associated with them. And now, I'd like to turn it over to Lorenzo, who's going to walk us through our mechanical design process.
Thank you. So let's jump right in. Quick overview of what I'm going to be talking about. We're going to go into specific design elements before we go into why the system center of mass is so important, and then some finite element analysis. You guys know what we're So first, for the air bearing mount, as you can see right here, it's going to be made out of aluminum. There's 3 points of contact to create a plane. We decided to use a Y shape to reduce the weight. So if you have a plate, it's going to weigh a lot more than reducing that excess mass that you don't need. If you look right here, you can see there's a coupler that is going to be printed out of SLA resin and then going to unite the base to the structural body, which will be on the next slide, as well as provide a surface to mount the plate down to the ERAU manipulator. As for the structural frame, it is composed of both aluminum in the S's as well as SLA resin on the sides. This is primarily to reduce weight while also getting that strength where we need it. As for the S shape, it allows for symmetrical mounting of the air tanks, which I'll cover in the future, and it also creates this usable space in the center. So that usable space is primarily for our momentum wheel station. First off, it's going to be made out of SLA, just like the other parts, and installed in that central cavity. The whole point of this is to make sure that our momentum wheel is actually in line with our Z-axis. As for the components that compose this station, you'll see that the top plate is made out of the SLA resin, as I said, as well as it includes the bearing rods for each of the linkages. The bottom plate has grooves in it for the motor so that the casings can actually slide into place, as well as holes for the motor shafts to go through. If I make it transparent, you can see that in the center, there is the momentum wheel as well as the momentum wheel mass. Since it's housed in there and that's directly in line with the Z-axis, the momentum wheel as a result is in line with the Z-axis, and that's what we wanted. Having your momentum wheel centered on your center of mass will actually help us be able to control and realize, how much momentum shifting in the axis upon which that's acting. And it also acts, the top plate also acts, as I said, as the beginning of our joint linkages and houses the motors. So to go into both the linkages, they're also going to be printed out of resin. They're going to install on each side of that momentum wheel station, as well as be composed of two separate components. To facilitate installation, we decided to have basically a body and then a top plate, so that when we're wrapping around that bearing rod, we don't have to try to squeeze these things in. We can simply line up the bottom and then screw on the top plate or fasten on the top plate, so that it's just a lot easier to install. Moving on to our second linkage, it's going to be primarily the same as the first with regards to components and how it's made, except it's installed on the end of the first link. The reason why it's different is because we have integrated a end cap. So the reason why it's round is so that we can, regardless of what angle we come to grab onto this object, as it's a rounded surface, we'll have a single point of contact. So rather than having to specify a specific angle that we have to approach an object, we have more variety in how we can approach this object to grab it. We don't have to center ourselves with the object. So moving on to how we plan on aligning these linkages. As our DC motors that we're using in our links, their encoders are not absolute, they are relative. So depending on where they start, that's basically our zero. So in order to increase our repeatability, we're making an aluminum alignment tool that's going to resist flex over time while also not fatigue. So we'll have this straight bar that stays straight as we continue to use it. So that bar will increase our repeatability by allowing us to line up our links before we begin our experimentation. If you look after the video on the right, you'll see the use of the bar. So the bar basically will slide through this body here, through the S. We'll be able to manually align the joints, remove the bar, and then resituate it. So on to the air tanks. So as I said before, the mounting holes for the air tanks are located on the top plate, or the top S in our structural frame. They're going to be made, the air tanks are going to be made out of aluminum, and their mounts are going to be printed with resin. Plan on manufacturing them in axe fab, made in-house, and they're going to have a capacity of half a gallon. This should allot a time of about 10 minutes for experimentation on the aircraft table. As for the electronic storage bay, this thing would be nothing if it didn't have a brain. So the casing as well as the racks you see here are going to be printed using Slate resin. It's going to be installed on top of that structural frame I showed you previously. And it's going to be composed of three components. You have two caps as well as a center wall. So if you look at the stacks, they're going to basically slide in from the top. A section of the previous slide will slide in from the top. And they're going to be primarily for our electrical components, our battery, our Arduino, our PCB board, as well as any other components. So these boards are going to be interconnecting to allow us to completely remove all of our electrical hardware, per se, and be able to perform tests without having to have to reach in and connect, test leads or whatever it be. So moving on to the system center of mass and why it's important. So if you look here, this is the best case scenario for our center of mass. It's with the links are aligned symmetrically, as you can see here. I've included a isometric view at the top for convenience. So looking from the top, you can see that the joints are aligned symmetrically, and that the center of mass is only displaced in the z-axis. So moving on to our worst case scenario, this is when the links are completely arranged asymmetrically, so the links are completely out in front. So this results in the greatest torque on our force torque sensor. And to calculate that torque, we can actually use the vectors, the vector for our center of mass placement relative to the base. So if you take that y distance and you go through and you know the total center of mass of our system is 6.34 kilograms, it's about 62 newtons, and we know that the distance is about 69 millimeters, we can go ahead and calculate the torque on the sensor. So the reason why the torque on the sensor is so important, because one of our specifications with regards to the force torque sensors that we should not exceed 1 Newton meter torque on the sensor in any of the axes due to saturation of the sensor. We don't want that. So this, as of now, this specification isn't satisfied, but we do have a solution. over the next semester, we'll work towards reducing the mass in the links, primarily because the further out you have mass in the links, you're just going to generate more of a torque. So we're going to try to move that mass closer to the base. Also by reducing the length of the links. If mass reduction becomes an issue, you can always reduce the length and just move that mass inward without affecting thicknesses and so forth. And then also software implementation. As of now, when the links are aligned in the front, there's actually there's a singularity when the links are completely out front. So we have to avoid that in our simulation anyways. So if the simulation cannot reach that point and simulate that singularity, we'll actually end up making our worst case scenario something more of an elbow effect in end. So now that we've talked about all the components, we're going to jump into the finite element analysis. But first, there's going to be several points of interest that I'm going to let you guys know. So primarily it's the bottom support. That includes the base upon which the air bearings are mounted, the central support, which includes the structural frame and the momentum wheel station, the link support, which is all the links, and then the tank support, which is those printed resin fixtures that I showed you earlier. So first, let's get into the bottom support. Here you can see I placed a 70 Newton load here at the center. That is the estimated weight of the robot plus a little bit. The total deformation, very small, smaller than a millimeter, and that is primarily in the x-axis and greatest at the center. So as for stresses, you see obviously the stress is going to be occurring in the actual arms of the Y. The max stress reported by ANSYS was about 8.13 megapascals. That is a lot lower than the yield stress of the aluminum that we plan on using. So that's not an issue. And then also it's primarily due to shear. Moving on to the central support, there was a 16 Newton load applied to the top. That's the approximate weight of all of our electrical components plus a little bit, as well as 2 4 Newton loads on each of the side posts to resemble or to embody the air tanks. The max deformation, again, even smaller than before and primarily in the x-axis. Moving on to stress, the maximum stress seen by the central support is less than a megapascal, and it is primarily seen in the S's, which are made out of aluminum. The yield of the aluminum, again, is 28 megapascals, so it's not an issue. As for link support, there was a 6 Newton load applied on the first link, and then a 5 Newton load applied on the second, primarily because there isn't a motor mounted on the end of this second link. The max deformation, again, less than a millimeter, so we're not concerned about it, as well as it's primarily in the x-axis. The equivalent stress, it's hard to see here, but it's inside these bearing points. The max was about 9.18 megapascals. The yield for the resin is yet to be determined. We plan on performing dog bone tests next semester to see exactly what we're working with. Published values online are nice, but in reality, once you print it, it weakens a lot, and we know that. So we're going to try to perform our own tests to figure out what those characteristics are. So finally, our tank supports. For this analysis, I put 4 newtons. This is a worst case scenario. They're half C's on the final product. We can't support our air tank with a half C. But right now, this would be the worst case scenario without a complete C with the centralized force right here. That was a force of 4 newtons. And the total deformation, again, less than a millimeter and in the x-axis. So for stress, the max stress seen by the S was 1.8 megapascals. Again, that's the aluminum, so we know what our yield's going to be. That was 28, so again, we aren't too concerned about any of the stresses seen by that top plate. And now I'm going to pass it over to Maddie Mark, who's going to talk about the electrical design.
Thanks, Lorenzo. All right, so I'm going to talk a little bit about the PSR hardware design today, and then I'll jump into the printed circuit board design as well. So starting off with our PSR block diagram, basically everything is going to stem from our microprocessor, which is the Arduino Do. That's going to go into a motor driver as well as a decoder, so it'll communicate with both of those, which will also communicate with our DC motor and encoder. So channels A and B will go into the decoder, and information will be sent back to the Arduino Do. One of our requirements is also to have onboard Wi-Fi capability, so we do have an XP Series 1 Wi-Fi module The Arduino Do will use UART pins to communicate through RX and TX. It will also go through an XV shield, which will take 5 volts in and regulate down to the 3.3 volts needed for that XV Wi-Fi module. Another one of our really big requirements is to have onboard power. As Andy mentioned, we don't want any excess wires or anything. So we do have a 12-volt battery, and then we regulate down to the 5 volts necessary to run that motor driver and decoder as well. And we will be using 3 GPIO pins going to each decoder, as well as 2 GPIO pins going to the motor driver and 1 PWM pin. As far as the power regulation goes, as I mentioned, we do have to regulate down to that 5 volts. So we're going to be using a DC switching regulator. This is an LDO replacement. It's simple 3-pin compatible. It's also up to 92% efficient and has a max current output of 2 amps. And the capacitors that you see there are required for stability. Those values are chosen based on the datasheet group recommendations. Moving on to why we chose the Arduino Do and the XV Wi-Fi module. As you saw, we do have 5 DC motors going, 1 for the momentum wheel and 4 in the links. So the design requires the use of 25 GPIO pins and 5 PWM pins. This is a lot of pins. There's not a lot of Arduinos that can handle that many pin outputs. So the Arduino Do includes 54 of them, 12 of which are dedicated to PWM. So that's sufficient for what we need. As an aside note, I've also used 3 of those GPIO pins as LED indicators for testing purposes. We have a red, yellow, and green one going. As Andy mentioned as well, we do have a control frequency of 100 hertz that we'd like to meet. The Do includes an 84 megahertz processor, and it's also 32-bit, so it processes a lot faster than any of the other Arduinos that we did testing on. And as I mentioned, the design also requires wireless communication capability. The XV Wi-Fi module is transparent, so it will appear as a serial port to both the computer and the Arduino Do, making it fairly easy to program through those UART connections. How this will be assembled, basically we will have our custom PCB on the bottom, and then the Arduino will hook on top of that. Extra tall headers, as are shown in the picture here, will be used to make sure that nothing comes in contact with each other. And then the XV Shield and the XV Wi-Fi module will hook on top of that. And the XV Shield will provide, the Arduino will provide that shield with the 5 volts, which will then regulate to the 3.3 necessary for the Wi-Fi module. Here is the DC motor schematic that we have, and we will have 5 of these. So as I mentioned in the block diagram, we do have the GPIO and PWM pins going into the motor driver, and then going into that brushed DC motor, and the encoder communicating with the decoder and back to the Arduino. And we have the 12 volts and the 5 volt rails on top, and the capacitors are simply bypass capacitors. For motor system components, we are using a Flowlu motor driver. This uses a TI H-bridge motor chip. It is a breakout board that includes current sensing and temperature regulation and everything like that. It also has a simple 2-pin interface for speed and direction, making it fairly easy to program as well. We are using Flowlu DC brush motors that have encoders attached to them. We are using a 100-to-1 gearbox for the motors in each link, while the one for the momentum wheel, we do not have a gearbox on that one. The decoders are custom picks provided by Dr. Isenberg to read those encoder pulses and return the numerical count. This is important. It does offload a lot of work from our Arduino Do, so we don't have to interrupt or pull as often as we would have to for 5 motors going at once. And it is important to note at this time we have built and tested this in the laboratory as of right now with 1 DC motor going. Moving on to the printed circuit board design. The printed circuit board is a really important component when thinking about building 2 identical robots. If we had breadboarded this, that's a lot of wires that you're trying to keep identical, a lot of things. Whereas a printed circuit board is going to be easier to keep the 2 as close as possible to each other. So what we have created is a 2-layer board with traces and components present on both the top and the bottom. The excess area is also filled with a ground plane. This provides a little bit more stability for the board. And then the ground vias connect the top and the bottom planes together. The trace width for the power is wide enough to handle the high current coming from that 12 and 5 volt rail, while the signal traces for everything else was made as wide as possible to fit on the board that we have. So here is the routing. You can see the 5 signals coming from each motor circuit. The red traces run along the top of the board while the blue run along the bottom. And following general printed circuit board design rules, nothing is at a 90-degree angle, and there's also no parallel traces on the top and the bottom of the board. And the bypass capacitors are also placed as close as possible to the ICs to avoid creating any stray or parasitic capacitance throughout the board. And as I mentioned before, we will be using extra tall headers to make sure that nothing connects. And what you see here is where that Arduino is going to snap onto the top of the printed circuit board. These are Phoenix connectors, so to make it easy to wire up and also to pull the whole board out for testing purposes, each DC motor will have an individual Phoenix connector on the board so that we can snap it in and then unsnap them, pull the board out, and snap them back in for testing purposes if we needed to. This will also keep the wires as consistent as possible between the two robots. Here is where the motor drivers and decoders will be. The motor drivers, as I mentioned, are breakout boards. They are through-hole components. So you can see the through-hole sections there, while the decoders are SMD parts. And I've also modified the silk screen to add labels up here that show which direction to plug those breakout boards in so that we don't accidentally put anything up upside down or backwards, because you can connect them in either orientation. And once they're on, they will look like that. You can see these are different directions, as I mentioned before, so that's why the silk screen is important. Here is the manufacturing preview. So we have the top side and the bottom side. And at this point, it is important to note that we do plan on building the entire system in the laboratory and prototyping it before we have a board spun. We want to have absolute confidence in a board before we purchase them and send them out to be made. All right, moving on, I will hand it off to Lucas to talk about battery design and the Parada schematic.
Thank you, Maddie. First of all, good morning, everybody. So as Maddie said, I'm going to be guiding you guys through battery design for the PSR, and then I'm going to jump into the ERAU schematic. So first, that's our PSR battery design. So the first thing we did here, we tried to create a block design which would specify all the components that we have in the PSR, so we have a better idea of what currents are going where and what voltage we're going to be needing. So second step, once we had all the block diagram for all the components that were needed, we decided to find those currents that were going to the specific components. So we found those currents. Most of them were provided by the data sheet of those components. Some of them we were able to find through some testing. So as this current right here, that's going to the decoder, we were able to find through testing. Also, this current going to the logic voltage for the motor driver, also through testing, and also that current going to our microprocessor, we're finding through testing too. So the main goal of the design was to find this current, the total current draw of that system, so we could find our battery. So we decided to choose a voltage for the battery as a 12 voltage, as was said before by Maddie. And then once we decided at 12 voltage, we could just track those currents down. So by Kirchhoff current law, we have that current, the total current that is being drawn here. The current going into the node, it must be the current going out. So once we knew that current right here provided by the data sheet that I said before, and once we knew the current up there on the microprocessor provided by testing, we could just try to find that I1. Sorry. So having that and having those currents through testing too, we found that current, the total current at this node right here. So once you have the total current right there, we can easily just find that power. So assuming this voltage regulator provides us a constant 5 volts throughout the whole time, and then we can easily calculate that power at that point. Having the power at that point, and as Maddie said before, we have a 92% efficiency on that voltage regulator. We can divide that power by 0.92 and find the power going into that voltage regulator, which will be specified at P1. Once we've done P1, we can then calculate that current going into that voltage regulator by using the 12-volt battery that we assumed on the beginning. And then we finally find that I1 with all the currents. We can just add them together and find our I total, which was about 1.28 amps. So now, once we've that done, we can also find the total power specified by the battery. And then we have a total battery of 1.2 amps hour. So to be safe on that specification, once we found that value, we decided to go with a battery that provides us 2.2 amp hour, just to be safe, so give us a bigger range of testing without like having to recharge it so as soon. So once with that done, we can finally just call it a day for the battery and then move on. So now moving on for the errata schematic. So the first thing I would like to point it out, this circuit is going to be provided throughout 3 times. Everything's on the green box will be repeated 3 times. The reason for that is that we have 3 motors in the errata as Andy specified before. So we're going to need 3 of this circuit right here to provide that. So starting right here with the power supply, which is a 12-volt power supply, it's going to be powering our motor driver, and then that motor driver is going to be driving our motor through channel A and B throughout the 2 terminals on our DC motor. And then that DC motor already has an encoder on it, which is good to point it out too. It is already provided for us, so we don't need to include that on our budget. And that encoder is going to be sending the data through channels A and B to our decoder, which, as Manny said before, is a custom PIC designed by Dr. I. And then it's also going to be being powered off by a VCC and a ground channel. And then that decoder is going to send that data back to our PC, which is going to be our workstation to reset data and a shift. And then that PC is going to be receiving that data through an AD-Link card. That is already as a digital input-output card and is already included on our PC workstation. Also, it's good to point out that our PC workstation is going to be controlling that motor driver to a PWM direction and a ground. Now, down here on our sensor circuit, good to point out that this sensor circuit is not going to act as an emergency stop. So it will let the motor, if we don't make a controller by ourselves, it will let the motor hit the end effector. So it's just that those sensors are just going to give us an idea where the motor is at and where positioning-wise, where is it placed. This circuit, this sensor circuit is a open collector circuit. So we needed that pull-up resistor at that point right there. Good to point out too that at this point right here, we have a signal which is 0 to 12 volts, which is 0 for low and 12 volts for a high. So I'm going to be talking a little bit more about this circuit on the next slide, which is the safest circuit for the PC and why it was needed. So as I said, this was the safest circuit that we had to design for the PC. So as I previously said, we have a 12 volts high in here. So if we send that 12 volts back to the PC, we can damage some of the components. So we had to lower that voltage down on the control logic to 5 volts in order to not damage our PC. So what we decided to do was place op amp, sending that signal to the non-inverting side of our op amp, keeping that current at 0 amps, so we wouldn't have any effect on our voltage levels. So once we have the voltage levels, we have a 12 volts right here. We can easily just calculate a voltage divider in there, and then have our 5 volts control logic sending it back to our PC without any like worrying about damaging any components on the PC. So moving on now, some errata testing. So the errata testing was needed just to make sure we had those motors working fine, and we were able to actually have a better idea on how to use them and how to control them on the future. So here on the top part of the schematic, we can see that this is basically the same as previously. The only difference here would be that the encoder is not sending any data back to our decoder, as we're just trying to see those motors moving around. It's also not being controlled by the PC. The PC is just programming that microprocessor, and the microprocessor will be the one that is going to be providing those directions to the motor and driving that motor. So the microprocessor is being powered off a 5-volt USB cable, and is controlling our motor driver to a ground, PWM, and a direction. So here's our input, which is a 25% duty cycle input. As we pointed out, there is an open loop. That means no feedback controller. And it's also a square wave input. So as shown on the waveform right here. So now here's just a picture to clarify stuff a little bit. So we have our microprocessor right here being powered off by a USB through the PC, already pre-programmed by the PC. And it's controlling sending that information to our motor driver, which is going to be driving our motors through those 2 terminals back there. So here's a little video to state that, as I said before, the PC out here sending that pre-programmed to our microprocessor sending that data to the motor driver, and our motor driver driving that motor to the 2 terminals by the end of the motors right here. And that's just a video of our testing. Okay, so now moving on, these are list of parts. I'm not going to go through in detail throughout all those components just for the sake of time, but I would love to specify a little bit more if you guys have any questions. Now I'm gonna send it to Tim Anderson, who's gonna be guiding you guys through to modeling and simulation.
Thank you, Lucas. So today I'd like to give you just a quick run through our entire modeling and simulation process, kind of from the ground up. And so we'll start with forward kinematics and some of the notation we use. So like some of you heard earlier, forward kinematics is the process how we describe the position and orientation of coordinate frames or points of interest on our robot in terms of our joint variables and geometry of the robot. And so to start with our vector notation, you'll see our vectors are underlined. R represents a position vector from point B to point C measured in some coordinate frame A. You should also be familiar with transformation matrices. Basically when we multiply transformation matrix out in front of one of these vectors, allows us to transform it between two coordinate frames. One type of transformation matrix is the rotation matrix. This is actually the only kind that we'll be using in this project because all of our rotations in this planar environment are about just a vertical z-axis. And so this function rot z of theta rotates a vector about the z-axis through some angle theta that you put in. And finally, a quick example how the forward kinematics process works. Say if we wanted to know this red vector, AARC, so that's from A to C measured in frame A, and we have these two vectors, AARB and BBRC, your first thought might be to simply add the vectors, and that's a good thought. That's pretty much what we do, but keep in mind that BBRC is measured in coordinate frame B. So before we can add them, we go ahead and transform that back into frame A, and then we can add them. So with that little bit of background, here's a look at the robotic schematic that we've created for, in this case, for the Harada, our robotic platform. This is what we look at when we're writing those equations for forward kinematics. So this is our Harada Cartesian manipulator. We have an inertial frame that's fixed relative to the Earth. And then there are two prismatic or translational joints. That's to get us in the X and Y direction of the Harada. Our joint variables are D1 and D2, so those are the offsets of those joints. That's how we measure them in meters. And then we have a revolute joint at the end effector of the Harada that can spin about the z-axis, and that variable is called theta h. Here at the end effector of the Harada is where we'll be mounting our PSR. And so let's go ahead and look at the schematic for the PSR. Here's our base frame on the PSR body. This is free to move, in the free-floating model, free to move in X and Y directions and rotate about its own z-axis. In the combined model where it's attached to the Harada, it can move in those directions also, but it's fixed to the end of the Harada manipulator. So we have some, our fixed dimensions are part of the schematic. We have a right and left arm, each with two revolute joints. You can think of them as a shoulder and an elbow joint. And then we have an end effector assigned, placed at the end of each arm. Additionally, the momentum wheel is attached to the base and rotates about the z-axis, and we call that variable theta m. And so with those schematics, we come up with our forward kinematics that we use in our simulations. Here's another way to look at the PSR. Here's kind of a top-down view. So again, you can see we have a right and left arm. You can see how we've placed our frames on the robot so that the z-axis is always up relative to our robot, relative to the Earth. And this allows us to always have a positive z-rotation, or positive angles are defined so that it's counterclockwise looking down on the robot for everything for consistency. And you can see the lines that are positive angles are defined for our joint angles. So with all that information, here's another way to look at the PSR and get into some inverse kinematics. So inverse kinematics are the way that if we have a desired or known end effector position, we can describe that position in terms of our joint variables and robot geometry again. And that's important to say if you want to move the end effector to some position in space, you need to know what position to command your motors to get there. So for us, in the PSR, this problem for each arm is pretty similar to just a very simple 2-3 planar manipulator, with the solution for which is well known and has been done plenty of times. The only difference is we have some fixed offset. The shoulder joint, if you will, is not located at the base frame of the PSR. There's some offset, but that's easy to deal with. We know it, and so we simply subtract it, and we use these new end effector position coordinates to actually perform the calculations. So here's a quick look at the solution. Starting from the law of cosines, we can find this term where these are the lengths of the links, and find that elbow joint value. You notice we use a tan 2 when we're doing this in MATLAB to go ahead and account for the different quadrants that the end effector might find itself in, and then we allow ourselves to select between a plus or a minus there for an elbow up or elbow down solution, where an elbow up solution is a positive joint angle with respect to the previous length. Elbow down is the opposite. That's useful for us. So, for example, if you want to move your end effector to one position, one of those solutions, elbow up or elbow down, may cause a collision with your robot with itself. So we want to select the other one. Once you have that angle, you can solve for the kind of the shoulder angles. That's not the same for each arm because our positive angles are defined relative to different axes in the base coordinate frame, and so we just account for that with some different negative signs there. Okay, so getting into velocity kinematics, there's a lot more to it that you can do, but all that's necessary for us is to know that we can simply take the time derivative of elements in our position vectors and transformation matrices, and then we just have to know that we account for the chain rule because the elements in both of these include our joint variables, which are functions of time as the robot moves. And so when we're implementing this in MATLAB, we account for the chain rule. So velocity kinematics allows us to naturally move into kinetic energy. Here's an expression that we're using for the kinetic energy of some body. So that can be one of the links or the base of the robot. There are a lot of expressions for this. The one that we're using has a couple terms you should be familiar with. BB gamma here is the vector of first mass moments of some body B. We find that by multiplying the mass of that body by the location vector to its center of mass. And then BBJ hat, this is a pseudo-inertia matrix, so it's closely related to the inertia matrix that you might be familiar with. So we go ahead and get the inertia matrix from our CAD model, SolidWorks. We go ahead and get that out of there and then just transform it this way for use in our equation. The kinetic energy equation can be looked at in terms of these three terms, where the first is our translational kinetic energy. There's also a rotational kinetic energy, and then they're coupled with that middle term. So once we found the kinetic energy for each body in our robot, we simply sum them to find the total kinetic energy for use in our equations of motion. So there are 8 degrees of freedom in this robot. We represent that with this vector of generalized coordinates, gamma. It's split up this way, where these first 3 are the base position and orientation of our robot, followed by the joint coordinates for the left and right arm and the momentum wheel. Interestingly, the way we're modeling this, these 3, so this is the free-floating model, those first 3, when you attach the PSR to the Harada, can be replaced simply with the joint variables of the Harada, the D1, D2, and theta H that I mentioned earlier, plus some fixed offsets. So that kind of shows you the motivation for why we're using that Cartesian manipulator. With all of that together, we can go ahead and start with Lagrangian dynamics and have our vectorized equations of motion. We have our vector of forces F, and then it's equal to our H matrix, which is our system mass matrix found from kinetic energy, multiplied by our joint accelerations. This vector D is our vector of centripetal and Coriolis effects, also found with kinetic energy. And then finally, we have our effects of gravity vector found with potential energy. So putting all that together, and then also including friction, these B and C matrices are diagonal matrices, where each element on the main diagonal is associated with one of those generalized coordinates, and B contains our viscous damping coefficients, and C is our Coulomb frictions and torques, Coulomb friction, torques, and forces. Sorry. We can decouple this to solve for each of our accelerations individually, and in our planar model, we're not concerned with gravity, so we can go ahead and remove it. It'd be 0 anyway in our case. We also need to include the motor dynamics. Because we're using DC motors, those are quite often modeled, and a lot of the characteristics are easy to find or given. So these are, again, diagonal matrices associated with each of our generalized coordinates, and they'll be introduced into our model on the next slide. So we take into account our armature resistance, inertia, gearbox ratio, the motor torque constant and back EMF constant, as well as, again, viscous damping and coolant friction, and then our gearbox efficiency. Some of these terms were given to us from the manufacturer, and some we've found via system ID processes that Andy will discuss later on in the presentation. So this is what our dynamics look like with the motor terms included. Notice that we're dealing now with a vector of motor voltages, not a vector of forces. And you can see those motor terms inserted, and we still have the H and D that we mentioned earlier. Again, we can decouple these to solve for our accelerations. So with all that together, I'm going to go ahead and show you what we've produced so far. So here's an example. This is a free-floating simulation of our planar space robot with just some arbitrary forces, arbitrary torques applied to the links. Notice how the base deflects when the arms move. We're not applying any forces directly to the base. That's what you'd expect in a free-floating environment, so that's good to see. We're implementing these models in MATLAB, and we're using a fourth-order Runge-Kutta solving method to integrate our equations in motion. It gives us quite a bit of control over the inputs that we're putting in, allows us to set our own fixed time step. We're using 1 millisecond for these simulations. And it also allows us to go ahead and wrap controller models around our MATLAB simulation. So this is just a very basic PD controller that we throw in there to prove to ourselves that we can do it. So this is driving those joint angles to specified angles. And so with all of that, I'm going to give it back to Andy to wrap us up with system ID and controller design. Thank you, Tim. As Tim said earlier, we do know our equations in motion for our combined robot and actuator dynamics very well, but we don't necessarily know all of the parameters involved. This is a perfect candidate for what's called a white box system identification process. These can be factored out into a vector of known joint space coordinate terms. These are sines and cosines of our angles or their derivatives, and a vector of constant unknown terms, which we'll call beta. If we run an experiment and sample at our sample frequency and record our input voltages and our output angles, we can actually generate these V and phi vectors and solve for beta with a least squares approximation, which ends up being the pseudo-inverse. In MATLAB, we use a robust backslash operator. Additionally, one of the most important milestones of this project was our ability to control a DC motor with a microprocessor. And so to do this, we've implemented a PID control law. It's important to note that our desired velocities are going to be 0. This is just a position controller. We intend to move to a trajectory controller later on. For this test, we are inputting a 5th Hertz square wave. This is just inputting a -90 or a 90-degree angle every 5 seconds. We're using a forward-Euler integrator to approximate the integral of our error up here, and then a differentiating low-pass filter for our gamma dot vector. This is important because if we were to just do a direct differentiation, it would amplify all that noise, and our low-pass filter would attenuate that and give us a more accurate result. A couple of features of this control scheme. The integrator is going to turn off when our input is saturated. This will prevent the windup on the integrator and help with our overshoot. Additionally, if we're in the static friction region, we performed a test to see when the motor will actually start turning at what voltage. If we're in that zone, we turn off the motor voltages just to save power and to prevent it heating up. It's important because we're on a battery in a power-limited system. This is a video of our controller working. This is just with an encoder on the end of the motor connected to our Arduino implementing this control law. And you can see a slight overshoot when it turns. We're going to analyze that a little closer in a little bit. These are the results from that experiment. There is a small amount of overshoot. We plan to eliminate this completely because in a robotic scenario, any overshoot in the motors is going to end up with you smacking into whatever you were trying to pick up. So we're going to take this to a completely overdamped system when we have more time to tune it later on and when we have the whole robot built. If we allow those integrators to saturate, this actually spikes to a 20% overshoot and oscillates for about 5 times as long. So having that wind-up prevention was a real boon. In addition, the rise time is a little fast. We plan on tuning this quite extensively later on, but the settling time is around 1.75 seconds. For the Harada control, we are actually planning on implementing the Model 3 force feedback controller from the papers listed earlier. This is the first of those. It takes these sensor forces, runs them through a rotation duct Z, and with a PID controller, sends those dynamics back into our system to drive those forces and torques down to 0. Additionally, this is the more advanced version of this. You can see it still uses the force torques from our sensor, but now here we calculate the center of mass of our system with a known mass to eliminate that drift and drive that center of mass down to its appropriate position. This should help us in the future eliminate some of that drift over time. For a high-level software flowchart, we plan to have two modes. One of these is to allow the user to specify joint angles, and another mode is to allow the user to upload a previous trajectory for our motors so that they can generate interesting frequency content for our force torque controller. It's important to note that both of these modes use the autonomous Harada force feedback control. This should just be running in the background and driving those forces and torques down to zero. In addition, one of our requirements is that we sanitize and validate user input so that what they input to our system will work and not break our machine. For the detail semester, we plan on spending most of our time testing our experimental setup and our Harada control to make sure that we're actually implementing our model-free force feedback control as closely as possible. The rest of the design is mostly linear, just assembling and manufacturing what we've designed this semester. As a review, we do have a complete preliminary mechanical design and structural analysis. We have a complete electrical schematic, budget, and parts list, a known forward and inverse kinematic solutions, a preliminary dynamic model of our system, a preliminary controller design and implementation, and a plan for the detail semester. And with that, I'd like to open this up to any questions.
Cool. Very nice, guys. A lot of information.
How much time do you have for get out at 6:30?
I believe so, yes.
Okay. So we should. Great. Thank you again. Very nice, guys. Let me find a couple of specific questions here. On slide 17, you talked about some of the specific specifications you have for the frequency of a lot of your components. How are these determined? They seem like obviously they're very round numbers, but what kind of backup do you have for to say that 1,000 is what you would need versus 2,000 or 500?
We were looking at the total resolution and frequency of our force torque sensor. Additionally, we have the benefit of previous research being done. The team before us planned on implementing a 1,000 hertz control frequency because that's what they felt they needed as well. And we
How did they feel that?
They from their testing, they looked at the frequency at which they were operating and realized they needed to go higher. They were missing some of the high frequency small forces and torques from that. And when we made our decision, we factored that in, and we also looked at the possible frequencies of every component that we had and tried to figure out what the bottlenecks would be, and figured out 1,000 hertz based off of that.
Okay, cool. Slide 27 is your kind of outline for your air tanks. So I'm a producibility guy, so I'm really curious how you plan to manufacture this. And then you don't mention anything about the maximum pressure that it's designed for and what the pressure drop over time is during your run.
So these tanks are going to be, as I said, manufactured in AXFAB. The plan is to, obviously, we can weld on the bottom plate without any issues. Welding the second plate is when it becomes an issue because obviously you can't weld inside of something that's sealed. So we plan to, that end cap's going to have basically a chamfer on it, and it'll sit in there, and then basically we weld inside the chamfer, and then that'll seal up the tank. And then obviously we can drill the holes for our valves and such. As for the pressure, taking into account some of the other capsules that are going on here, some of the propulsion teams, they've also made their air tanks in-house. They're actually containing oxygen. So, and they're operating up at the range of, I think, 200 plus PSI. Ours are dealing with about 120, and we're going to operate at about 80. We're going to regulate it down to 80.
Right. Have you done any analysis though to say what thickness tank we need, what testing you're going to do before you put that thing up to 120 PSI the first time to make sure that it's passing your sort of leak check or the other structural type test? I'm a little worried.
Oh, I think
talk to some of that.
Exactly. So we haven't done any particular designs yet. We know that this half-gallon capacity is based on the dimensions of the tank. As long as the tank does not basically width or mounted, they're mounted symmetrically. So regardless if they grow in length or they grow in depth, it's not an issue. As for the analysis for whether it can contain the pressure, that'll be done at a later date. Ordering the material for the tanks is probably dependent on those calculations, and also what's available. Obviously, ordering this tank, I believe this tank is about a foot long. If ordering 1 foot of tube, obviously no one just sells a foot of, I think it's.
But I guess, I mean, as far as the thickness goes, I mean, have you figured out what thickness of specific pipe or tube you're
So
putting
a
in?
minimum of a 1/4 inch, and that would be.
I mean, you've done some pressure calculations to say that.
Yeah, earlier, I didn't include that.
Okay. Yeah, so that's something to look at. I mean, I think there's probably a lot of commercial off-the-shelf systems too, particularly for other programs, that would make me feel a lot safer about this aspect of it. And then I didn't see anything related to, so you have a 10-minute runtime, your pressure's gonna be decreasing during that, so your efficiency of the air bearings, right, that you're using go down. Have you made sure that whatever 120 PSI it sounds like is gonna be capable of doing a 10-minute runtime?
Yeah, so since the bearings operate at 80 PSI, we're keeping it up at 120 and we're regulating it down. So over time, obviously, our pressure is going to drop.
Right.
And based on the volumetric flow rate of the bearings, we determine that even as that pressure drops over time, we'll still level out at about 80 PSI once we've hit our 10-minute mark. And after then, it's not safe to operate the bearings.
Okay, so you have done some flow analysis to your MDOT to make sure that you're gonna be okay as far as your runtime. Okay, that was one of the things, and kind of related to that was the structural analysis for this is on slide 43. Can you highlight where the forces were applied in this ANSYS model?
So that would be, that is directly on this end right here. So eventually, obviously, it's not going to be an open sea because your air tanks are just going to fall out. But that's exactly where the force would act, and that's without the additional support that would be introduced if they were mounted at the top and bottom. So this top joint would also help with some of that stress. Right now, that forward Newton force is only right here on the tip of this.
Okay, so in this model, it would have been really great for a lot of these to show where your forces are being applied, and particularly what constraints you're using at your joints.
Okay.
The other one that kind of brought that up was your first one, which is on slide 37. In this one, are you fixing those 3 outer where the air bearings are located? I guess the video maybe is on the next slide, but or here it is. What are your constraints that you're using for this? I'm curious, mostly because of the plastic part you're using in the middle there is taking a lot of the load. So can you tell me about your constraints?
Yeah. So so the constraints being used are a frictionless surface or frictionless constraint. So basically, all the air bearings are free to move in X and Y. Actually, this coordinate, this is fun. So they're free to use in Z and Y, and then cannot move in X because it was on an air bearing table. Right. Those bearings wouldn't be able to displace through the table. As for the constraint, this was not allowed to move in the X or Y direction, okay? Z or X direction. So basically fixed. So that force was only straight down and no components in those other directions.
Okay.
And then the deflection was, and the stress was measured in these links. And then, yeah.
I guess what I'm worried about here, and pardon if I'm not familiar as thoroughly with the air bearing setup, is the angle at which those 3 air bearings meet the table, I believe must be kept at a very, very tight tolerance. And seeing this bend lets me, I'm not sure from this analysis that how much that bending is allowed and what those air bearings can take as far as that angle goes.
Okay.
And then the centerpiece is plastic, right?
Mm-hmm.
Is your aluminum pieces really significantly weaker that it's not showing up in this to say that those joints that as it's coming in, you're gonna be yielding your plastic eventually make your plastic malleable at that point?
So I failed to describe that the aluminum actually goes all the way through, and that the plastic part is only on the surface.
So it's one piece aluminum all the way
Yeah, it's
through?
one piece, yeah.
Oh, okay. Okay, so it's not 3 individual parts then?
No.
Okay, that would have been helpful to be more clear. Okay, thank you. I'll pass it on because I know there's probably lots of questions. Very nice stuff. Yeah.
Good job, guys. Just a couple quick things. So on slide 12, I think me and Bryce both saw this earlier, and I just kind of want to stress, you know, the sensors at the highest possible frequency, it doesn't really constrain your design, it's freedom of interpretation. So for requirements, kind of want to constrain your design. So that's fine here, but just keep in mind for later on, that would want to refer.
Does that make sense?
So for the air bearing mount, Bryce kind of talked to us, so that's on slide, go back to construction analysis. 38. So, one of the things that I thought, so you applied the load straight now. So was that need to be more severe than any of the cases where you have some of those lateral forces? Did you look at those at this stage, or?
So I looked at that in the way of load path. So if, so our primary concern is the weight of gravity. So while there may be other forces introduced, the primary concern is that this thing will flex under the mass of the robot, especially having those arms out there. That's basically the weakest point right in the center, and that's where we're concentrating our mass.
Yeah.
So,
I think that, so your case, so the load case you're most concerned about design driving is the weight of the load.
yes.
Okay. I think that was pretty much it, except for just one quick thing. So on slide 87. So is there any reason, so what was the reason for using the robust backslash? Because I've recently faced something where I had to use the more Penrose. Did you look at, are you getting the same solution for both methods, or?
Yes, sir, we are. The backslash in this case, because it's an overdam system, defaults to a QR solver in that one. Because it's a rectangular matrix, it defaults to a QR solver, which ends up giving us the same as the pseudo inverse, but it is it's a lot faster. So
Okay. Nice job.
Okay, next. Go to slide 59, or pick on Lucas a little bit. So at the top there, you say the microprocessor regulates to 5 volts. Is that the correct statement?
I believe so.
Okay, is your microprocessor a power source?
No.
Okay, so you got a board, right, the Arduino Duo? And so that board has a regulator on there, but the microprocessor itself is a digital device. It's not something that's going to supply power. So just some details in there to watch out for. Another thing, when you look at where the current is flowing to the motor, what's it going through first?
Chain encoder.
Is the encoder getting 1.22 amps?
No.
No, okay, so you probably want to rejigger that a little bit so that the current's going to the motor and then the encoder's receiving some power from elsewhere. You also said this is a battery design. You might want to use something more like power system design or something like that, because you're not actually designing a battery. So just a couple details that I think if you bounce off your group, you might catch. Flip the next slide. And the same thing here, we got the power supply there with the 12 volts. And you got 2 of them wired down and 1 of them wired to a negative. It might be good to explain which one's the positive and negative terminal on that actual 12 volt power supply. Because I figured out the bottom one's the ground, but you just have 3 lines there and it's a little confusing there. The other thing, the sensor circuit, I was really confused on. Now, maybe it's because I'm an electrical engineer, but I feel a little better if I saw the transistor in there and that you were getting an external, I guess it's a switch of some sort that you're dealing with. If I saw that, then I would understand more how that was actually controlling it. Because to me, just with the box there, it was really hard for me to know what was going on. And I was talking to Dr. Davis, and he saw me, that I was trying to figure out what's going on. And then just a few things here. You say your protection to the PC. You're not actually protecting the PC, right? You're protecting the arm from crashing. Is that correct?
The 12 volts, I think, would damage our 8-link card, as I said before. So that would probably damage that card.
Okay, so what you're trying to say there is that you're stepping it down so you're not getting 12 volt on.
Yeah.
Okay. But I think there's a few little oddities in there, and some of it I know you're not a native UNS resident, so I think just having your group members read through there and make sure that some of the uses that you have, like with versus to on the next slide. And so it says that Arduino is programmed with, it makes it sound like you're using the PWM to program the Arduino Due rather than to do this. And then also your 25% duty cycle doesn't match up with the duty cycle you got shown there. That's what duty cycle do you have in the graph? Is that 25% duty cycle?
I'm at the graph,
Okay, so
I figured, 0.25 would be, where 1 is 100%, 0.25 would be.
When you do say 25% duty cycle, that's a 50% duty cycle. So you got just some things in there.
I'm sorry, this wasn't clear. The duty cycle was amplitude that we're feeding in the PWM motor, not the square wave of the input signal over time. So
Okay, so those are, the 25% duty cycle is referring to something different than that graph.
Yes, sir. The amplitude of this here is the duty cycle of our motor controller, which uses PWM. It's feeding in 25% of the energy from our power supply, not the, this over time, out at 6 seconds, this is the square wave of our system. It could be more, I'm sorry.
If I can clarify, I believe what you're saying is you're referring to a 25% amplitude,
Yes, sir.
not a 25% duty cycle.
Duty cycle.
So it would have been right to say it's 25% amplitude, 50% duty cycle.
Yes, sir. Sorry about that.
So just some details in there, and I think a lot of that, if you just kind of a little more review within the group, would be gotten cleaned up.
Sounds good, thank you.
I'm gonna pick on the resume. That's what he can say. On slide 21, if I understand correctly, the blue parts are gonna be SLA resin,
Yes.
but they're just square blocks.
Yes.
Seems a very poor use of SLA resin. You could take a block of aluminum, plug out whatever weight you need, that's just a spacer.
Yeah.
So you're gonna be spending a lot of time in the SLA trimming that thing that you could just block and just do all, you know.
Not gonna argue with that. That's completely correct. That is completely
And then-
a possibility, yeah.
Why are those parts S-shaped?
So in order to get out our air bearing, or not air bearing, our air tank mounts far enough away from the center that we could mount a momentum wheel, and also maintaining symmetry, we created the S design to basically, as you can see, any mass of the top link in one direction is counteracted by mass in the bottom link in the other direction. So basically, primarily for that symmetry about the z-axis, or in the plane.
Structurally, I would take a hard look at another solution to that problem, because that's a very dramatic violation of the third law of structural design, which is short straight load path.
Okay.
Torsion and structurally, that's just a nightmare.
Okay.
So you save a lot of weight. But it looks cool.
It does look cool.
Okay. Just on presentation style, maybe it's just me, but I really don't like the looping videos. I find it very distracting trying to listen to what you're actually trying to talk about.
Okay.
And then, yeah, the air tanks, a really huge deal. Prices come with that. Buy them. And you're not looking for anything special. You're gonna find something off the shelf. It's design your support structure around it. There's no sense in doing it.
So we did consider that. That was our initial approach to this. It was not, we did not jump to this. It was over some iterations. And the available air tanks for the PSI that we're working with, the smaller they get, usually for paintball, they're too small for, their PSI is overkill. And then we also would need to be able to supply that pressure in the lab. So as of now, we do not have that ability to supply things like 3,000 PSI, whatever, of pressure into this.
Why would you do that?
That was the minimum charge. You actually have to buy pressurizers just to fill up some of these small paintball air tanks.
Why can't you find a tank, a commercial tank, similar size, pressurize the design pressure you're talking?
We did research it, and the only thing I can speak to is that we had a great deal of trouble trying to find one. With the specs that we need at a half gallon, at and the trickling factors and the geometry of some of the tanks that we were looking at, and the mounting features of the tanks. Obviously, we could design our own, but we did go through that iteration, and we determined that when we spoke to AXFAB, it was completely doable. So we could again swap back to purchasing the tank, but as of now, decided to.
So if you do build this thing, I require that you do a proof test of this. You cannot trust products.
Yeah.
Of course, not X-raying or doing any of that, so you must do a proof test on it. So speak with the propulsion guys, and background on how to do that.
Okay.
You know,
Of course.
And I would also recommend to talk to some of the AE teams that I know have dealt with similar situations before.
Exactly.
They should be able to provide you part numbers for the regulators and stuff.
And then on the capacity, are you just taking the mass flow rate PR equal rho RT and to calculate your bleed down the tank pressure, or are you assuming adiabatic, so you're accounting for cooling of the gas and losing?
We didn't account for the cooling of the gas. We just accounted for the differential pressure between what's in the tank and atmosphere.
Assuming it's only set ambient temperature.
Yeah.
Might be, if you're bleeding it a lot, it will cool down, so it won't be ambient temperature. And
Yes.
then also similar to the comment about that block there on slide 42. All those pieces, you talk a lot about them, and you're worried about the weight of it, they're all those pretty simple geometries. Using this regular, you could probably take out weight.
By changing infill.
Making a sheet metal.
Oh, okay.
Fabricated block there. And then, if you go to plastic, you mentioned that you're gonna be doing testing, but you never told me what the color value was. So you have a positive margin, you're keeping this color and stuff.
I don't have that value memorized, but through experience, that value is very well inflated and isn't reasonable because it usually decreases by a factor or two. So I did not include that value because I didn't want to lead astray, but yeah, there are published values and I've taken a look at those. Just off the top of my head.
At least below those.
Yes. As far as like for rigid resin, which is the stronger of the resin fan, we are within that. Yeah, I think it's a little more brittle, but for what we did, the rigid resin did meet this parameter.
Can I do two quick ones? Slide 25. You mentioned the routed in cam for singular point of contact. Is there any intent to contact anything? So I didn't hear any description of contacting something. So what's that about?
We left it open. We wanted to make it sort of like an actual space robot would be within reason. Without designing an end effector for it, we left just the tubes in there so that if we decided to run a test that we could pick something up or at least grab it. But as of right now, I don't think we have any plans with that experiment. That was just there for the future.
Just wondering why I was want that out there. They'll have a single point. On slide 46, you mentioned the Wi-Fi module a couple times, but I didn't hear any description of what data are you going to be communicating over the Wi-Fi signal. So what's the point of having that? What data is going which way?
I think I glossed over it in my section later on. We plan on using the Wi-Fi to send back our joint space coordinates for analysis after our tests. In addition, we are transmitting our preloading trajectories to the robot. So we do need to communicate it with it at some point during our tests. We just plan to use it before and after and run autonomously between.
All right, 2 seconds that remain. I guess I'll just make comments so we have no time for questions. First comment, looks like both motors are the same on the joints, right? Why? So if you want to see the weight, I'm gonna guess that the little further up would require as much torque, smaller motor. Second comment, you talked about relative encoders. If I recall correctly, those heads encoders that you have an index on them, you could use that to transform relative to absolute, save yourself a fair bit of work.